Thank you.
He's professor of physics and history of science at the Massachusetts Institute of Technology. Thank you very much, Professor Kaiser, for participating in our emblematic series of conferences, Hablemos de Física.
Thank you.
I would also like to thank the United States Embassy in Madrid and the Asociación Juvenil Española de Estudiantes de Física, especially its president. Thank you very much for their collaboration. We have worked together in many meetings, and it is always a pleasure to collaborate with them. This year we celebrate the centennial of the birth of Richard Feynman, one of the most influential physicists of the 20th century. Professor Kaiser will present Feynman's most important scientific contributions in the context of his life and times. Let me briefly introduce our guest. As I mentioned before, David Kaiser is professor of physics and history of science at the MIT. His award-winning books include Drawing Theories Apart, the inspection of Feynman diagrams in post-war physics, and also How the Hippies Say Physics, Science, Counterculture, and the Quantum Revival. He co-directs a research group in early universe cosmology within MIT's Center for Theoretical Physics. Fellow of the American Physical Society, he was elected for outstanding publications that combine technical mastery of 20th century physics with a deep knowledge of recent development in the history, philosophy, and sociology of science. Professor Kaiser has received MIT's highest award for excellence in teaching. His work has been featured in Science, in Nature, but also in the New York Times, the New Yorker magazine, and the National Public Radio, and also the BBC. So thank you very much, Professor Kaiser, for participating with us in your conference. Thank you.
Thank you. Thank you so much for inviting me. Hola, gracias. Gracias, buenos dias. I'm really delighted to be here today, and I want to thank the department and the dean for this very kind invitation, and also the physics students, Society of Physics students, and my colleagues at the embassy for arranging this really lovely visit. Thank you. So I want to talk with you today about a figure whose work I'm sure is well known to every one of us in the room. So I want to help us understand partly where some of these ideas came from within Richard Feynman's own life and career, and point towards some of the ways in which we still grapple with many of these ideas today. So as you know, we're now right on the cusp, right on the edge of the 100th anniversary of Feynman's birth later this week. He lived not quite 70 years. He passed away just shy of his 70th birthday. And as you know, he led a rather eccentric, unusual life within science and indeed beyond science. So today I want to remind us about some of his greatest contributions within our own field, again, things that are often quite familiar to us, and then also backtrack and trace a bit more of his own trajectory, his own meandering world line, we might say, that brought him to some very stark issues even beyond the physics classroom. So I'll talk a bit about Feynman's own early years, how he himself began a path towards studying physics. I'll mention only a couple of his most consequential contributions. There are many, many more, but in the interest of time, I'll only talk about a few of them. And then I'll zoom out a bit more to think about some of his larger legacy within physics, but not only limited to physics. Richard Feynman was born in New York City in 1918, but not in Manhattan, not the sort of skyscrapers exciting central part of the city, not here. He actually was from this very tinier spot called Far Rockaway in the borough of Queens, which is really much more like a small town than like the big city. So it was technically part of New York, but he was really out of the way. It was more of a kind of beach town, right on the water, still fairly rural, a small town upbringing. And He had a younger sister, has a younger sister named Joan Feynman, 9 years his junior. Both Richard and Joan went into the sciences. Joan became a very accomplished astrophysicist in her own right. Richard Feynman recalled years later that both he and his sister got great encouragement to pursue scientific careers from their parents, in particular from their father, from Melville. Melville came to the United States as a young boy at 5 years old. He emigrated from Eastern Europe, from Belarus, and he never had a chance to pursue higher education himself, but he always pushed or encouraged his children to follow a scholarly path, and in particular, to be curious about nature. So Feynman had these really quite lovely recollections later in his life about walking around the beach or the wooded areas, the kind of forests near their house. And his father, Melville, would always encourage Feynman to try to figure things out on his own. Don't read a book and memorize the fancy Latin titles for different species of birds. Watch what the birds do. What are they doing? Why do they do what they do? As Feynman later recalled, his father would say, let's look at the bird and see what it's doing. That's what counts. Melville's own job was in the garment business. He sold clothing, mostly uniforms for postal workers or police and fire department. And again, Richard Feynman years later would say that itself left a deep impression on the young Richard Feynman, that Feynman's father, Melville, would always say, don't get too impressed by formal authority. That's just a person in a uniform. Remember where those uniforms come from people like his own family. There's nothing special, nothing magical about putting on a uniform. And this Feynman would use that story to talk about being, wary of formal authority. So Feynman was a very gifted and curious young person. We know from both his own autobiographical accounts and other historians who've studied the correspondence from the time, that Feynman taught himself things because he was sort of too eager to learn things even before he got to them in school. So he would go to the local library and borrow books on calculus when he was a very, very young person, long before he got to calculus in school. We actually have his notebook from that time. It's quite a treasure. He got very concerned that a lot of the notation was dumb. He thought the way that people handled things like trigonometry, sine of x, let's say, or calculus, he thought these were foolish notations. So he'd invent his own, and we have records of that in his notebook. He was quite gifted, and then indeed, when came time to choose university, his first choice was to attend MIT, the Massachusetts Institute of Technology, outside of Boston. He was accepted there, he went to study there, and again, very quickly became a kind of an outstanding student. He did very much better than the average, partly because he and a small circle of friends would keep trying to puzzle things through on their own. And again, we have notes, some of their study sheets have survived. So they wouldn't just do what the textbook said, they would try to rederive things in their own special way. For his undergraduate thesis, Feynman worked with the great solid-state physicist John Slater, to try to apply these still pretty new ideas from quantum theory to understand the forces in molecules. If we take quantum theory seriously, a very young Richard Feynman asked, what implications does it have for the forces that keep atoms bound together in molecules? This was an original enough piece of work that was published in the Physical Review as he was a senior, a final year student in undergraduate studies. And around that time, he decided he really wanted to pursue a career in this. He had caught the physics bug. There was no getting around that. Now, this was, of course, the Great Depression in the United States, in Europe, many parts of the world. So Feynman's father, Melville, who had worked very hard and with very little, was concerned about what a foolish notion this might be of going to graduate school in physics. Some people might still think that's a foolish notion, but it's especially dangerous or curious in the Great Depression. So Feynman's father wrote to one of Feynman's teachers at MIT, basically saying, is this a good gamble? Is my son Richard good enough in a very, very tough job market to try to make a career, a living in physics? It's a really charming letter. My son Richard, he says, is finishing his schooling here next spring. Now he tells me he wants to go and do more studying to get still another degree. This was not a standard thing to do in the 1930s. I guess I can afford to pay his way for another few years, but what I want to know is it worth it for him? Is he good enough to deserve the extra schooling? And thankfully, the response that Feynman's father got back was, yeah, he's pretty good. He is good enough. We don't encourage everyone to go to grad school, but this kid seems to have what it takes. And luckily, the message got through. So Feynman did pursue graduate studies. He went to Princeton in New Jersey, leading university, much smaller than MIT, a little bit more out of the way, made to look more like the grand universities in Europe than this rather hulking modern thing in Boston. And Feynman got to work with the remarkably talented young John Wheeler. Wheeler, again, a name probably familiar to all, certainly most of us in the room. Wheeler was only a few years older than Feynman himself. Wheeler was a very young professor at the time. The age difference was something like 6 or 7 years total. Wheeler had just joined the Princeton faculty the previous year. He was a very new, very young professor. And they hit it off and had some marvelous, marvelous interactions, which Feynman and Wheeler each recalled many years later. Well, in the midst of his studies, of course, things became very complicated. Europe, as you know, had been engulfed in World War II for quite a while, starting open war already by 1939. As you know, the United States had not joined the war effort, not right away, not formally. That changed in December of 1941, following the surprise attack on the American naval base in Hawaii, the Pearl Harbor. A Japanese surprise raid that caused tremendous damage. The very next day, the United States declared war, formally entered World War II. Feynman was still in his graduate studies, still pursuing his PhD at the time. One of the things that changed almost overnight after the surprise attack was a huge escalation in the United States of a very top secret project called the Manhattan Project. Again, by now I'm sure a name that's familiar to you. This was still quite top secret. There had been little efforts along the way in the United States before the US joined the war, but after the attack on Pearl Harbor, this project, like so many others, became a very high priority. The project became sprawling. Here's a map showing just some, not even all of the installations across North America, some in Canada, most in the United States, devoted to this project, which of course was a top secret classified project to try to develop nuclear weapons, to try to harness these strange nuclear forces for a new kind of weapon. It involved an enormous number of people, most of whom had no idea what they were working on. There were huge numbers of workers at many of these sites. And the cost was also quite extraordinary. Adjusting for inflation in today's currency was on the order of $25 billion, a very massive project. It was led by a curious combination of people. The US Army General Leslie Groves, a career Army man, a kind of engineer by training, and then this very young, very inexperienced theoretical physicist named Robert Oppenheimer, who never had to organize a Department T, let alone a huge sprawling project. A very curious combination of folks. So very soon after the US entered the war, there was an effort to recruit young physicists and young physics students to work on this still highly classified top secret project. It was hard to recruit because I couldn't even really talk about what the project was doing yet. So Feynman was approached by a young Princeton professor, nuclear physicist, Robert Wilson. Wilson went on later to help found the Fermilab National Laboratory, but at this point he was again a young professor of nuclear physics, and said, basically, I can't tell you all the details, Wilson says to Feynman, but I think you should do this. This is an important challenge that we need to focus on. Feynman at first declined. He thought he had no interest in working on a weapons project. He thought this was the wrong thing for physicists to get involved with. But then, at least in Feynman's own recollections, he spent the afternoon thinking more about this and convinced himself it would be much worse, Feynman said, if Hitler got nuclear weapons before anyone else did. So that same afternoon, the very day that Wilson had approached him, Feynman changed his mind, agreed to work on this project, and that very afternoon was already set to work on isotope separation. Again, folks here will probably know rather well that by this point, the chemists and physicists in various parts of the world had realized that there are distinct isotopes, distinct flavors of heavy nuclei like uranium. The most commonly naturally occurring isotope of uranium, U-238, its atomic mass of 238, is basically inert. It's certainly stable. However, a variant that has 3 fewer neutrons, so the same number of protons, the same place on the periodic table, but 3 a little bit lighter, fewer neutrons, this could behave very differently than its heavier cousin. And that much had been figured out haltingly by the very end of 1938, 1939, still pretty fresh news by the time Wilson was trying to recruit Feynman in 41, 42. So Feynman, like many others, began wondering what physical process might we exploit to take advantage of that very tiny mass difference, roughly 1%. Chemically, the two substances would, of course, behave indistinguishably. So you can't use chemistry to separate the two isotopes. You need some physical trick. Are there ways to accelerate the uranium and then bend them in a magnetic field? And because of the different mass, they'll have different arcs, different paths in a magnetic field. Or maybe make a gas of them. It turns out to be a remarkably toxic, messy gas, uranium hexafluoride, which will eat through many metals. And again, try to take advantage of the minute difference in mass to try to sift one from the other. These are the kinds of things Feynman was working on literally the day he agreed to join the project. Not long after that, he moved to the new laboratory in Los Alamos, New Mexico. It was still under construction. You can see here's a car being stuck in the mud. This was not a gleaming facility. It was mostly huts, temporary structures that were thrown together rather hastily. It was, of course, a top secret facility. Here is Feynman's own badge he had to show to get in or off site. He joined the T division, the theoretical physics division. His boss there was Hans Bethe. Here's Bethe's own badge to get in and off the site. Bethe was originally from Germany, trained with the great Arnold Sommerfeld, a few years older than Feynman. Bethe had left the continent and resettled in the United States after Hitler rose to power in Germany. Bethe's wife was Jewish. He didn't think this was a good place or a safe place to be. So Bethe then became one of the earliest recruits to the Manhattan Project and indeed was in charge of the entire theory division, theoretical physics division at wartime Los Alamos. One of the challenges that Bethe assigned to Feynman, and indeed to many people, was to try to figure out some way to calculate the processes of nuclear fission. By this point, people knew that U-235 was different than U-238. They had some inkling about the kinds of fission products. What happens when a big, fat uranium nucleus is split, is fissioned by a neutron? What are the kinds of chunks that are left over? How much energy on average is released? And crucially, it turns out they knew by this point that on average 2 neutrons would be emitted among all the junk that comes flying out of a broken apart uranium nucleus. So the idea was maybe these neutrons could then start a chain reaction. That one could nudge a neighboring uranium nucleus, and the process might unfold very, very rapidly. So Feynman was given the task of trying to figure all this out quantitatively. And he began making doodles that might start looking familiar to some of you. Here's one of his, at the time, classified internal reports. My colleague Peter Gallison, a really marvelous historian, found this in the archives and has analyzed it in a brilliant article. So Feynman began making space-time diagrams that might register with some of you in the room, given where we know he's going next. He tried to break apart the process into little constituent pieces and to find some clever way to add up all the different things that could happen to neutrons in this kind of nuclear matter. So sometimes a neutron might simply escape. That's this one up here. This one might just fly away and have no other business with these uranium nuclei. That event had a certain likelihood, a certain probability. There was a different probability for a distinct event. One of these neutrons might bombard into a uranium nucleus but get absorbed. It might not start one of these nuclear reactions. It might simply be absorbed and change the isotope of uranium. That has some distinct probability to happen. Or a neutron might hit a uranium nucleus and actually cause fission, and so on. So Feynman broke the problem down into these little constituent pieces, began tracing these trajectories through space and time, and then, rather ingeniously, figured out a way to break up the problem quantitatively using these hand crank adding machines, these Marchand calculators. Remember, at this time, there were approximately 0 electronic computers on the planet. In fact, the very first ones were being developed for other uses at Los Alamos at the time. But Feynman had access not to the room-filling enormous so-called electronic brains, what they called then, but rather to these rather modest hand-cranked computers, and to a team of assistants, most of them young women, most of them wives of many of the researchers at the laboratory. And he would organize these kind of coordinated teams who would do one mathematical operation over and over again. So one person's job was to turn the crank to accommodate this probability and then hand a piece of paper to the next person. He literally broke this up into human chain computing. He became the youngest group leader at Los Alamos at the age of approximately 24, maybe 25 years old. He caught the eye rather early of his colleagues. Again, as many of you probably know from Feynman's own stories, he had other things going on in his life at that time as well. He had married his high school sweetheart, Arlene Greenbaum, and she traveled with him to New Mexico. Unfortunately, Arlene had tuberculosis. This was before there was any kind of cure for tuberculosis. So she was not able to live at the laboratory. She actually lived in various facilities, kind of hospital facilities around the laboratory. And as Feynman wrote rather movingly in some of his own autobiographical collections, they would stay in touch by letter. Now, Arlene was, like Richard Feynman, rather playful, didn't always respect authority very much, so they began writing coded letters. They would write in cute little codes because they knew that all the letters going in or out of the laboratory were being read by censors. So rather than saying, yes, yes, we understand it's very serious, we better play by the rules, they said, I'm going to write coded letters and see if the censors can crack them. And that didn't always make friends, but that is indeed what they did. Meanwhile, Feynman also famously began learning or practicing how to pick locks and open safes, which is sort of a cute thing to do to change, to let the time go by, but not everyone thought it was cute if you're breaking into safes that hold top secrets of the Manhattan Project. So in fact, he told these stories in his own words many years later. We now know that the FBI found this not so funny, and in fact they had a dossier, a once classified dossier on Feynman, where people wrote in saying, don't trust this person, look what he did during the war. He sent coded messages from a top secret laboratory and he broke into safes. So luckily not much came of that, but indeed it was filed away and taken for a time rather seriously. Tragically, Arlene Feynman died in the end of June 1945. The tuberculosis finally overwhelmed her. And just 3 weeks later, Feynman himself had yet another dramatic event in his own life, dramatic for the whole world, but I think especially so the timing was quite a lot to absorb for the young Richard Feynman. So just after Arlene died, the project at Los Alamos was preparing the very first test of a nuclear weapon, the so-called Trinity Test in the desert of New Mexico, to see if this new concoction would really work. This was exploded in secret in the desert early in the morning of July 16th, 1945. We have a remarkable first-person account of that test from Feynman himself. He wrote his mother a letter. You'll note he couldn't send it for several weeks. He wrote the letter, but then could only mail it later. And it's really one of the first people ever to lay eyes on the mushroom cloud, on this now iconic explosion from a nuclear device. He talked about the sky lighting up, the range of colors, the shaking you feel physically when the blast wave emerges. It's really, I think, quite a startling letter. He even ends by talking about this looks like a mushroom. Remember, no one had seen that before. He already associates this to a mushroom cloud. Just weeks after that first test, of course, the whole world would soon learn about these new mushroom clouds. The weapons were used by the United States against two Japanese cities, first Hiroshima in early August 6th, 1945, 3 days later on Nagasaki. Just 5 days after that, after the Nagasaki bombing, Japan surrendered, bringing the Pacific War to a conclusion. So there's a great deal of continuing debate and analysis. Did the bombs end World War II? Were the Japanese about to surrender? Were the bombs unnecessary? This is very complicated. And indeed, some of my colleagues have written very, very interesting full-length books on that. These are things that historians and physicists and other scholars have been able to learn and return to decades and decades later as more and more materials became available from the Japanese side, from the Soviet side, from deep within the United States. No one knew that, or very few people knew all that at the time. The reaction in the United States at the time was, thank goodness the bombs were used, the war is over, many lives have been saved. The bombs were horrible weapons and killed many people. But the consensus at the time, although, again, it's more complicated, I think, today, the consensus at the time was these weapons ended the war and saved lives. And that made people like Richard Feynman into overnight celebrities in the United States. They were seen as heroes for having brought these indeed destructive things to use to end an already quite destructive war. Feynman, however, was not so sure even himself. He wasn't so sure this was all good or all bad. And again, I find a rather striking recollection that he recorded years later. About as soon as the war was over, he left Los Alamos, began moving on with his career, but he recalls sitting in New York City, went back home, and thinking about the consequences if one of these new weapons was used at home. Right? Imagine New York City or Madrid or anywhere else. He would think of these zones of destruction and think about what really have we done? This sat with him and it made him, by his own account, really quite depressed. So unlike many of Feynman's colleagues from Los Alamos, who then spent much of the rest of their career involved with nuclear weapons policy, with disarmament, with international relations, Feynman detached. right? Feynman had a sort of a different reaction from this experience. And he really set these things aside, tried to set them aside, and did very little work on these topics for the rest of his career. Now, he had already impressed people like the scientific director, Robert Oppenheimer, and Hans Bethe and others. So when the war was winding down, there was a race on to see who could hire Richard Feynman first, which university could grab this young star. Here's a lovely letter that Oppenheimer wrote to his colleague saying, "We better nab this person." Feynman is by all odds the most brilliant young physicist here at Los Alamos, and everyone knows this. He's a man of thoroughly engaging character and personality, extremely clear, extremely normal in all respects. I don't know what that means. And an excellent teacher with a warm feeling for physics in all its aspects. Unfortunately, even Oppenheimer was too slow. Oppenheimer's subordinate, Hans Bethe, had scooped up Feynman already. So Feynman agreed to follow his boss, Hans Bethe, back to Cornell in upstate New York, and he joined the faculty right after the war. So once he became a professor, he was still, by his own account, still rather confused about his experience from the war, some would even say depressed, and he began returning to thoughts he'd had to sort of largely set aside during the war, things he'd begun talking about with John Wheeler for his PhD back at Princeton. And he wanted to understand the interaction of light and matter. He wanted to know, for example, why do like charges repel? Why do two positive charges push each other apart? Is there an accounting of that basic fundamental fact at a deep microscopic quantum mechanical level? It was in that context that he began returning to these very handy space-time diagrams. I say returning because these really are just like those neutron diffusion type graphs he'd made in a very different context in the midst of the war. He began charting these possibilities out in space and time. He said, let's break down the problem. What are all the things that could happen? Well, an electron, a charged particle, could move from point 1 to point 2 over here. A charged particle could shoot out some force-carrying particle, a photon, a single quantum of light. That photon could be absorbed by another electron. He just wants to plot this story out as it would unfold in space and time. He says, here's what's happening at a deep fundamental level. Here's why like charges repel. Because this electron is moving along in some direction, has some momentum. At some point, it spits out this force-carrying particle, a photon. It's now emitted a blast of energy and momentum in that direction. So Feynman says, what's bound to happen? Just like a hunter firing a rifle, the hunter must feel a recoil, must have a kick in the equal and opposite direction. So this electron was moving in one direction. Now it's had its course change. It has to change direction. A little while later, that blast of raw energy, that photon, will encounter the second electron. It will now repulsion. Now that in itself wasn't, of course, brand new. The problem was that people had tried to do similar calculations before the war. Here's an example from one of Werner Heisenberg's very talented graduate students in the mid-1930s, Hans Euler. And they realized that these electrons could do all kinds of things. They could trade one force-carrying particle, one photon. They could trade 2 or 3 or 7 or 100. And so the algebra quickly became impossible to track. Here's just a little bit from Euler's published article in 36. Not only was the algebra a huge mess, but they kept getting nonsensical answers. When they added up all these integrals back in the 30s, they found something very, very sick in their calculations. They'd say, what's the odds, what's the probability for 2 electrons to scatter? Well, at the simplest approximation, if they only considered one force-carrying particle exchange, they could get a straightforward answer. Maybe it's 73%, maybe it's 25%. But once they began incorporating any of these more complicated scenarios, they didn't find a little change to their calculation. They found infinity. So what are the odds for 2 electrons to scatter? It might be 25%, it might be 99%. It can't be infinity, right? Their equations had broken. And this was basically where the state of the art had ended before the war. Feynman was aware of this, and he said, well, maybe we can do better. So he had his new bookkeeping device, these new funny little kind of idiosyncratic squiggles to help him track them. He said, first, let's use this not just to tell a story, let's use this for our mathematics itself. This diagram for him became a map to the mathematics. So he would translate each little piece of these diagrams into a very specific mathematical expression. There's some odds, there's some probability, or really a probability amplitude, let's say, for an electron to move entirely on its own from here to here. Okay, put that in your equation. There's some different probability for an electron to emit a photon over here. Put that in your equation and so on. So he could map the corresponding algebra. And then he could conquer some of these more complicated situations, 2 photons, 3 photons. When he did that, he found that many of the terms that had confused the folks before the war, that led to these infinities, actually exactly canceled. that if you have a cleaner map to the algebra, then you find effectively plus infinity and minus infinity, and before you knew how to separate them, you got lost in all the jumble of equations. Finally began to find you should be able to get a finite answer after all, if you know how to map the different ways these things can interact. He said many years later, I was in my pajamas, working at night, on the floor with the papers all around me, these funny-looking diagrams of blobs and lines sticking out. And I said to myself, wouldn't it be funny if these diagrams really are useful? I mean, they really refer to him just a strange, eccentric little bookkeeping device. Wouldn't it be great, he says, if people start using them, if the physical review has to print these silly pictures? And of course, now we know they did. So Feynman first shared these insights with colleagues at a private workshop, only about 25 or 28 participants, soon after the war. Now, he didn't have a great time there. His lecture followed an 8-hour presentation by Julian Schwinger. So I don't remember if I'm booked. Is this a 9-hour lecture today? This one's not going that long. No, we don't have the room that long. So imagine having to follow the great master, the great wunderkind Julian Schwinger, who used an entirely undiagrammatic approach. Schwinger had no patience for pictures, but had found his own way to map through this messy algebra. And he indeed had found these cancellations of the infinities as well. Schwinger had found his own way to make what we call renormalized or finite calculations. Feynman then was given half an hour at the blackboard following that virtuoso performance. It did not go well. He was repeatedly interrupted. At one point, Niels Bohr got up from his chair. The great Niels Bohr, co-inventor of quantum theory, took the chalk from Feynman's hand and says, "You understand nothing." That's not good feedback, right? So Bohr says, you can't draw space-time pictures. The uncertainty principle says, the very foundation of quantum physics says we can't map the position and momentum of a quantum particle. If you don't understand that, you understand nothing of quantum theory, let alone all these other funny equations. That's not encouraging. Paul Dirac, another great architect of theory, says, well, he asked about what physicists call unitarity, again, probably familiar to you. Basically says, if you do your trick and add up all the contributions, does the probability add up to 1? You've told us it's not infinite. The probability is nonetheless well-defined. And Feynman says, what's unitarity? That's not encouraging to his audience, right? He's not having a good time of it at all. So in general, people were completely confused about what this very strange, wacko set of ideas were all about. And Feynman, once again, was disappointed and some would say depressed. Luckily for Feynman, he did have a much more receptive audience back at Cornell. There was a young mathematics student named Freeman Dyson. Dyson was a British young mathematician who'd come over on fellowship to study at Cornell. He mostly wanted to study with the great Hans Bethe, but he began falling in and spending more time with Feynman. He sent a series of really extraordinary letters back home. This is a reminder to say, all students remember to write home to your mother. This is a good lesson. And Dyson's mother actually saved all the letters, and decades later he got them back and actually just recently published them. It's quite remarkable. Dyson very kindly shared them with me when I was working on my book, and now we can all enjoy them. And he gives us a portrait of what it was like with this young, unusual figure, Richard Feynman, at Cornell. And he says he's the brightest of these young theoreticians here. He's that rare species, the Native American scientist. I love that phrase. And he says he's just effervescent. He's always bubbling with ideas. He bounds in the room with his latest brainwave. He expounds it with the most lavish sound effects. Dyson was enamored of this Richard Feynman, and he invested the time to figure out what was going on with these diagrams. They drove cross-country together, a 6-week journey that summer. Right after Feynman gave that very disappointing presentation at the workshop, Dyson had him all to himself for weeks and weeks and weeks to pick his brain. And it was Dyson who really kind of found the rules that Feynman had stumbled upon. Dyson is the one who starts translating him into the familiar physics that quantum physicists had used for a generation. He began writing up these much more straightforward translation tools. When Feynman draws this, it means that. Feynman might wave his arms and dance around, but he's really just doing this. It's familiar after all. It was Dyson's kind of recipes to convert Feynman's quite powerful but unfamiliar diagrams into the more familiar language of quantum field theory. That's what really caused these things to spread. In fact, as I write about in my book, we have these unbelievable, exponentially rapid takeoff of these diagrams only after Dyson stepped in. After Feynman gave his presentations, nothing happened. In fact, it only stirred more confusion. But then Dyson, large behind the scenes, had a remarkable role in not just translating, but kind of proselytizing for the new approach. So during this time, Feynman's fame, thanks in part to Dyson, began to grow, and the California Institute of Technology in Southern California hired Feynman to their own faculty. They were rebuilding their science faculty. They wanted this young star. So he moved there in 1950. He got married. Arlene, his first wife, had died. He got married to a second time to a woman named Mary Louise Bell. This relationship did not last. I love this. Their divorce actually made the local Los Angeles papers. There were two reasons why they got divorced, according to the newspaper. Feynman played the bongos all day, and he did calculus all night, neither of which seemed to be a good recipe for a healthy relationship. So indeed, they got divorced just a few years later. Soon after that, Feynman met Gwyneth Howarth, and they got married. They had 2 children. They would drive around Pasadena in my favorite van of all time. That's how you knew it was Feynman driving down the street. And indeed, his home life became once again quite happy, but with some quite distinct bumps along the road. Well, now that he was at Caltech, he didn't just have a new family, he had new colleagues as well. One of his closest colleagues, who joined the faculty soon after Feynman did, was Murray Gell-Mann, again a name I'm sure that's familiar to you here. Gell-Mann was several years younger than Feynman, but was also this sort of the one to watch, a person full of ideas about nuclear particles and nuclear forces. And they often had developed a very friendly rivalry. They interacted all the time, but also always wanted to be first. So together they were talking about not just the force between electromagnetic forces, between, say, charged matter and light, but rather these other even more exotic nuclear forces, like the weak force that causes things like radioactive decay, weak nuclear force. So Feynman suggested at a conference of particle physicists in the mid-1950s, maybe we've been too quick to assume that nature is always exactly symmetric. It was Feynman who first suggested, it was only a suggestion, not a worked out theory, that some of these nuclear forces, in particular the weak force, might break what everyone assumed was a very solid symmetry of nature, so-called parity symmetry, or sort of like reflection symmetry. The young theorists T.D. Lee and C.N. Yang had already been thinking about the weak nuclear force in a much more focused way even than Feynman. They picked up on this suggestion combined with their own thinking, and they proposed a new experiment that if this reflection symmetry, parity, is actually not upheld in the weak interaction, maybe you could really measure that. Maybe there's a new experiment to do. They convinced their colleague, Xian Wu, a great experimental physicist at Columbia, where they were based, to do a very particular kind of experiment, and basically to put a radioactive nucleus in an external magnetic field, and then basically flip the handedness, in effect, hold the whole experiment up to a mirror. If the force was mirror symmetric, then you should have no change in the outcome of that experiment. But building on Feynman's suggestion, they said, well, if this symmetry does not describe this particular nuclear force, you should have an inversion. The radiation will actually behave quite differently if nature does not obey that symmetry. Wu's experiment, a brilliant experiment conducted just in a few days, found exactly the result that Feynman had wondered about and that Lee and Yang had been more careful with. This was really shocking. So here's a news conference at Wu's university by the great Isidore Rabi saying this is a rather complete theoretical structure, has been shattered to the base. I mean, that just reminds us how really shocking this was to the experts. I think many of us have gotten used to symmetries and symmetry breaking, all these things. In the mid-1950s, this was really literally headline news. We're not sure how the pieces will be put back together. So Feynman now got really excited. Not only had this curiosity been taken seriously, but now there was some new physics to describe. So he went back to work with his colleague Gell-Mann, and together in very rapid order they produced what is to this day basically the theory of the weak interactions. Their theory about that accommodates this broken symmetry at its core and describes in a quantitative way how certain nuclear particles with spin must interact via the weak force, and it must do so in a symmetry-breaking way. And he said years later that as proud as he was of his work in electrodynamics, the funny squiggles, the diagrams that fill the journals, he said really that was just translating someone else's work into words he could understand. This work on the weak force, Feynman was convinced was his greatest legacy. He found a genuine law of nature, he was convinced. And he said, there was a moment when I knew how nature worked. It had elegance and beauty. This, Feynman thought, was more important even than his work in electrodynamics. Many, many other things to talk about. I won't give an 8-hour lecture, so I'll move on. Soon after his work on the nuclear forces, Feynman changed directions again. And he started working on gravitation. That was actually really weird. Many, many, many physicists at the time considered gravitation, in particular Einstein's very beautiful theory of relativity, general relativity, as being a subject for mathematicians but not for real physicists. It seemed separated from new experiments. It seemed different in its orientation than all the other work in physics. And so general relativity had been admired but kept apart in the years after Einstein's own great triumph. Feynman went back to saying, gravity is kind of important. It is one of the basic forces of nature, and on some scales it determines the fate of everything. So Feynman began going back to it, and in his own way, rewriting Einstein's work in Feynman's own idiom. So we tried to think of it as, for example, like the other forces. Could we think of it as an exchange of particles? Could we think of this not as this rich geometrical structure, but as something like force-carrying particles knocking into other particles? Could we make it look like the other forces they'd already studied? He began doing some work on this, publishing some papers, and then perhaps even more important, giving a series of lectures at Caltech for advanced students, for PhD students, where he just remade the subject of gravitation from the top down. And again, we can hear kind of echoes of his father's advice. Sure, Albert Einstein is a great authority, but why do we have to trust authorities? Why is Einstein the only way to think about Einstein's own work? And so Feynman, more so than most people at the time, began rethinking relativity, and that was enormously inspiring for many of his students, who then went on to carry this much, much further. The last example I want to mention of some of Feynman's sort of broader physics horizons came a few years after that. This is now the early 1980s. Feynman had been puzzling through quantum theory since his very youngest days, even his undergraduate thesis. But by the early 80s, he realized maybe it's not enough to just study quantum theory on its own. What if we try to put quantum theory to work? What if we don't just admire this as some weird thing? What if we do something with it? So he gave this very, very well-remembered talk at a conference in the early 80s, 81, saying, let's turn to something like quantum entanglement. Again, a subject likely well known to you here. This sort of quintessential quantum mechanical behavior. We can have a pair of particles, twin particles A and B, created in a special state. Let's call it a singlet state. They can be blasted out from that source and encounter two different measuring devices, identical boxes. And as we flip the lever here and perform different kinds of measurements, spin along the x direction, spin along some other direction in space, for example, we're going to find that the answers between the two line up in a really strange way. They line up in a way that Einstein himself had called spooky action at a distance. Einstein thought this was like a ghost story. This can't be true of the world. Feynman didn't invent entanglement by any means, but he was among the first to see this could be a resource, not just a curiosity. He said, if these particles A and B have all these very strange, essentially quantum mechanical behaviors, if these correlations are robust, what if we use those to do our computing? Computers, after all, standard computers like my laptop, use sort of basically classical logic rules to push electrons around to try to add stuff up. What if we don't use classical rules of logic? What if we use the rules like these entangled particles behave? We have a whole richer structure to think about. And again, indeed, he wrote this up. He encouraged several of his students. And this was one really essential kick along the direction to what was now a flourishing industry of quantum computing, or quantum information science more broadly. And again, I just want to highlight that Feynman was translating well-known stuff back into his own language, making sense of it, and then trying to say, we should think about it this way. What happens if we change our orientation? So by this time, Feynman was, of course, not just well-known and respected for his work within physics itself, he'd also become a really beloved teacher. In the early 1960s, he and two colleagues decided to remake the undergraduate curriculum for the entering students at Caltech. There was a common complaint that was common then, it's still common more than 50 years later, the complaint that we have all these remarkable mysteries and joyous things in physics, the grandeur of relativity, the curiosities of quantum theory, and yet we have our introductory students go through really rather old physics before they can get to this weird, cool, exciting stuff. So they wanted to get really, really young undergraduates involved in modern physics from day one. And so they rewrote the entire introductory curriculum for this. They wrote these up as lectures on the Feynman Lectures on Physics, 3-volume set. Again, I'm sure well known to many of you. I love this letter. I found this in Feynman's archives at Caltech. Once word got out that Feynman was doing these lectures, many publishers wrote to him saying, let us publish your lectures. Usually when we want to write a book, we have to say, please, publisher, please, will you consider my book? And so they said, dear Professor Feynman, you're writing a book, let us take it first, right? It's really a nice reversal. And here's now, once they agreed and they had rough drafts of the book, a sales rep was given the rough draft and sent to Europe to say, hey, you might buy this for your class when it's available next year. And the sales representative, wrote back to the publisher saying, give me more Feynmans. This stuff is selling itself. Everyone's excited about this new approach. He says, great enthusiasm in every department. Give me a Feynman once or twice a year and I will do my job. I don't know who signed them up, but I suggest you owe this man, not Feynman, but whoever was smart enough to get Feynman to sign on, a fine turkey for his Christmas dinner. And indeed, the sales representative was right. This became an enormous success. These books sold 130,000 copies in 6 years. That's not quite Harry Potter level of success, but that's success in publishing. And indeed, of course, they're in print and much beloved to this day. Feynman himself deemed this a failure. He said after a few years, they tried to put too much in the first years. Students really do have to learn how blocks slide down planes. You have to do some really good standard classical mechanics first. And yet the books have a life today not so much as a first entry for physics students, but for us, for more advanced students, to go back and see how did someone like Feynman make sense of otherwise familiar material. And the books have this wonderful life even to this day. So around this time, Feynman became in high demand to give public lectures, not just to students, but to non-scientists all around the world. Very famously, he gave these lectures at Cornell in 1964. They were videotaped. This was long before YouTube. These are horrible, horrible black and white videos, often out of focus, meant to be seen on a screen that's this big. I guess we all watch things on a screen this big again, but they used to call that television. It's not just phones. Really horrible production. It was basically Feynman waving his hands at a blackboard for an hour, 6 times in a row. And he became a sensation because he was just so bubbly and so excited about this work. And so examples like this began to get his name around even beyond physics circles. That was amplified, of course, the next year when he shared the Nobel Prize for his work on electrodynamics. Well, what often happens is these lectures would be recorded and transcribed. Someone else would type out what Feynman had said and then published. So Feynman's job was to show up, give a great story, have it be recorded, and then leave. And then Feynman's colleagues or assistants would do the hard part of writing it up, editing it, getting it published. And indeed, that's how all of these books made their way into print. Feynman's, these lectures from Cornell were published in a book called The Character of Physical Law. Years later, he gave similar series of lectures, and so on. So Feynman's sort of renown began to grow even beyond physics, in large part because of his extraordinary lecturing power. Now, after this rather stark experience at Los Alamos, Feynman did not follow most of his colleagues into arms control or policy or worldly matters. In fact, as I say, he kind of pulled back. So much so that years later, Vicky Weisskopf, my colleague from MIT, made a famous bet with Feynman, saying, Mr. Feynman will pay the sum of $10 to Mr. Weisskopf if at any time during the next 10 years, Feynman has held a responsible position. I wish I'd made that bet, right? So Feynman won. Weisskopf paid him 10 years later. He made an easy $10 because he really, really was immersed in the physics and not in these other, frankly, serious positions of responsibility. He had a similar concern, Feynman had a similar concern with the National Academy of Sciences. He was elected to this very elite body, one of whose roles is to advise the US federal government on matters pertaining to science and technology and medicine. But he wound up resigning. He thought his main job was to give out more honors and not really to do real science. So Feynman, you see this throughout, even decades after the Manhattan Project, is still kind of trying to remain apart from these rather serious, weighty matters. Nonetheless, he was pulled back into service one last time. Again, many of you may know. On the winter morning of January 28th, 1986, the Space Shuttle Challenger launched from Florida. And about a minute and a half later, it went through this catastrophic explosion. This was quite chilling. I actually watched this live on television. There was a school teacher on board, the first ever school teacher, Krista McAuliffe. They had TVs in practically every school in the country for young kids to watch this great day. Imagine having to explain to rooms full of young people that this just happened live on television. This was jarring. This was shocking. It was shocking to me. So despite trying to stay away from matters of responsibility, Feynman really relented eventually and agreed to serve on this investigation committee along with a number of experts in engineering and aerospace and so on. And once again, he was concerned that there was a kind of blind respect for authority that was getting in the way at NASA, and as far as Feynman was concerned, was getting in the way even in the investigation of NASA. And so quite famously, he'd been tipped off by a kind of dissident engineer. He didn't do all this himself, but he knew exactly how to make his case. He was enough of a showman. He knew how to talk with his audience. So during a televised press conference a month later, he took a piece of this rubber, of this O-ring, that had been used in these solid rocket boosters, and he dipped it in his ice water, much like over here, to make the point visibly, to make the point unavoidable, that this material loses its elasticity, changes its properties if it's in cold weather, like it had been rather cold even in Florida on that launch day. And that maybe that single, simple change in the material's properties was enough for the seal not to seal the right way, for superheated gas to escape, and indeed to lead to this. That was found to be the sort of the culminating moment that led to the explosion, and Feynman was convinced that it took this kind of healthy disrespect for authority to bring that out in the open. That was really his last time in the public eye. He had already been battling cancer. He'd had several surgeries by that point, and he died about 2 years later in February of 1988. So now, on the eve of his 100th anniversary of his birth, how do we make sense of this character? What do we think about for this individual? On the one hand, he has literally changed the way we think about the world. He's changed the way we see the world. I love this cartoon. This cartoon says that if you're going to go explore the Amazon jungle, you better have a good map. Now, of course, the Amazon jungle is this strange cacophony of nuclear forces, and the map are these simple-looking Feynman diagrams. We have to see nature the right way. My colleague Janet Conrad, who's a brilliant neutrino physicist, has a sculpture of a Feynman diagram in her office, of which I'm very jealous. You can now get them on coffee mugs, on pillows, on postage stamps. So these diagrams are everywhere, not just in our hallways and our blackboards, but really everywhere. Of course, Feynman's role as a teacher, but also as a kind of inspirer, not just to physics students directly, but to audiences well beyond the confines of physics itself. I think that's a legacy that we can continue to admire and continue to benefit from many years later. And finally, even if it might have been reluctant in several instances, he's someone who did answer the call to national service and with remarkable effect when he was a very young person and then indeed very late in his life. So with this, we take all this jumble of contradictions and curiosities together, and we have really a remarkable legacy to think about here 100 years later. Thank you.